So in the last video, we defined a double integral over region R to be a limit of this sum, where this first part f of xjk, yjk is a sampling of points, and the f value at each of those points we multiply by delta a, that is the size of our subdivided regions. And we take the limit as those subdivisions get smaller and smaller, as we have more and more of them. So how should we think about each of those terms in our sum? Well, plugging in a point into the function f gives a height of the graph, gives the z value, and delta a, this is the area of that subdivided region. So we could think of that as a base. That is, we're multiplying the area of a base, a rectangular base, times a height. This is the volume of a prism, or the volume of a box. So what we get is that this Riemann sum type thing, we really can think of this as the next dimensional analog. Instead of adding together the area of bars, we're adding together the volume of prisms, of 3D prisms or boxes. So when we think of it that way, we see that the double integral measures volume under a surface. Well, we should say signed volume, because it's possible that one of these could dip into negative territory. Let's take a look at CoCalc and see a graph of that concentration function we saw in the last video. So here's a graph of that concentration function. As we should expect, it's highest right in the center at the origin, where the chemical is spilled, and then it dissipates pretty quickly as we get away from the origin in both the x and the y directions. And here is a picture of a 5x5 subdivision where the height of each of these boxes is the value of the function in the center of the box. So you can definitely see how it conforms to the shape of the graph, but it's not a great estimate. But what we're claiming, and this is sort of the philosophy of the Riemann sum, is that if we add together the volume of these boxes, that's an okay approximation for the volume under this surface. And then if we change the number of divisions in each direction, well, you see we have a much finer subdivision and actually a much better estimate. So it's still an overestimate. We can see that because these boxes poke out above the surface of the graph, but there's a lot less of an overestimation. Let's see if I can not break my computer by bumping it up even further. Yeah, and as it gets finer and finer, it becomes harder to distinguish the boxes from the surface of the graph. But this is a picture of a 40x40 subdivision of that rectangle. Now, let's look at a few other examples. We won't solve these. We won't actually take the integrals to evaluate them, but let's decide if the integrals should be positive, negative, or 0. So for all of these, we'll let this region R be a square that goes from -1 to 1 in both the x and the y directions. And my question for you is, again, what's the sign of the value of these integrals? Let's take a look at CoCalc to see their graphs, and then we'll come back and record our estimates. All right, here's a graph of the function fxy equals x. we can see that a portion of it is above the xy plane, a portion is below the xy plane. And you can think about what the integral on this region would be. A graph of the function 3/2 minus x squared minus y squared. Graph of the function x squared plus y squared. So this sort of green floor here is the xy plane. And the Pringle-shaped graph, x squared minus y squared. So what do you think? Are these integrals positive, negative, 0? So for the first one, the integral of x, we have half of the surface is above the xy plane. That is in positive z territory. Half of it is below the xy plane. These halves will cancel out and give us an integral of 0. The next one, we have the top of a paraboloid opening down. This whole thing is above the xy plane, so the volume under it will be positive. We've got another paraboloid, this one opening up. It touches the xy plane at the origin, but it never dips below, so the volume below this also positive. And the last one is a saddle, and I think if you look at it long enough, you'll convince yourself half the volume is above, half the volume is below the xy plane. So these will cancel out and give us a signed volume of 0. So that's how we can think about a double integral graphically. In the next videos, we'll see how we can compute these symbolically or algebraically.